Hi, my name is Josh, and today I'll be talking to you about thundering herds of iPhones in your neighbourhood and what you can do about them. Let's begin. The theme of this talk is emergent synchronicity. That is the way that things unexpectedly or unintentionally synchronize. To get things going, I'm going to begin with a small thought experiment for you. If the scenario seems familiar to you, then just pretend you don't know the outcome. Let's imagine that it's the 9th of August 2016. And you are responsible for running the 5-yearly census that night. To save money, this time you get to run it on the internet. It's expected to be a busy night, with upwards of 10 million households completing it online at some point. Like the real bureau, you might prepare by outsourcing to IBM, putting your requirements into contracts, and so on. Or maybe you don't. But at minimum, I hope that you too would have run load tests on your site. So, are there any problems that will happen as a result of these preparations? And I don't mean outsourcing to IBM, it's not the problem. I don't have an opinion of them either way. What about the expected maximum load of 250 forms per second? It sure sounds like a lot of capacity. It's equal to 900,000 forms per hour, and that definitely sounds like a lot of capacity. Furthermore, this estimate was provided by the Bureau of Statistics. And surely statistics people would have some reasonable estimates. They're not the Bureau of Meteorology. It turns out that if you need to submit 10 million forms, and you can do it at exactly 250 forms per second for however long you want, then you can be done in just over 11 hours. That's much less than a day, so it sounds like it'll be enough. There's just one big problem. The problem is, it turns out that it's basically impossible to force 10 million Australians to do anything at an aggregate rate of exactly 250 per second. For one, we can expect the rate is going to fluctuate. For some periods, there's going to be relatively few forms submitted, and at other times, there's going to be many. In order to hit that 10 million in one day, it's more reasonable to assume the peak rate could be a lot higher than 250 per second. But before we answer that question, aren't computers magic? Surely there's going to be plenty of headroom to handle any temporary spikes. Well, unfortunately, we can't be kind to the ABS on this one. Without further testing, there's no guarantee of having any headroom at all. To find out how much headroom there is, you should perform some stress testing, which is basically load testing to the point of completely overloading the service in order to find out. It's not obvious from the Senate inquiry report whether the ABS did this. Perhaps they wanted to, but it was a matter of putting numbers into a contract, and they couldn't decide on a number bigger than 250. We don't know. What number would you put? Just how much bigger than 250 per second could traffic fluctuations to the site actually get? So to answer this, let's do the same thought experiment, but from a different perspective. Once again, we find ourselves on census night, but now we're the ones who need to complete it at some point. And we have better things to do, honestly. The Rio Olympics are on the TV, so for the purposes of this thought experiment, we'll be watching the telly. You're watching the telly, do you A, wait for an ad break, a change in the sport, something Australia isn't competing in? Or do you B, take one for Team Australia and pick a random moment to do the census? Well, I think you would wait for an ad break, right? That's what I guess. I didn't survey anyone to arrive at this, and perhaps I should have. But I predict most people would choose option A because, constraints permitting, humans tend to do things at moments that are most convenient for them. The Olympics had around 1 million viewers that night. Does this mean the site should have handled 1 million forms in the last possible second? I don't know. It's certainly possible. It's possible they would have gotten 10 million forms submitted, 11:59:59. Ultimately, we likely won't have any idea what the true possible peak load would be until perhaps the next census is run, because the 2016 census had a prolonged outage starting around 7:30 p.m. that night. While there were plenty of fascinating aspects to the 2016 census to discuss, ways to make fun of the Australian government for it, the one thing I'm trying to get at is that while individual human behaviour can be hard to predict, seemingly random, and developers tend to assume that all humans will behave perfectly randomly, the truth is that human beings are surprisingly good at synchronizing together in aggregate. They do this without electing a leader, following orders, or even intending to synchronize at all. And it happens not because of some sinister conspiracy to force people to synchronize by poisoning the drinking supply, but happens simply because it's allowed to happen. As a special case of Murphy's Law, we might say that anything that can synchronize will synchronize. I realize that a fair number of you are probably app developers, but just quickly, if you're fortunate enough to have control of the server end, there are all sorts of tips and tricks for you to help you scale up your service, deal with load spikes, and to help you make friends with your accounting department by reducing cloud spend. If you focus more on the app side, though, that's great, because that's what the rest of this talk is going to be about. Whatever you happen to work on, though, remember that if your app is predicted to be popular in a particular country, it might suffer a success disaster when everybody in that country finishes work at the same time to go play with it. Hopefully you've already considered what your app will do when, not if, but when, the service supporting the app has an outage, because it's going to happen. Network cables get cut, data centers have electrical events and thermal events, but have you considered what happens when that service you depend on is restored? Surely everything goes back to normal right away? Well, let's say your service is just fine and receiving traffic, has an outage for a bit, and then it's restored. During the outage, the service obviously doesn't receive and handle any traffic, but what does the traffic level look like when the service is back? Is it going to be the same as before, or is it going to be a lot lower? It depends what is happening with all the clients. Paradoxically, you might find the load could be a lot higher than normal. There are lots of reasons this can happen. For example, the app might be coded in a way that retries a lot more than you expect. Or the users might be retrying a lot themselves because they really, really want to use your app, and how dare you have an outage, you evil person you. They might just be able to get through if they refresh one more time. How your app is coded can greatly affect both of these effects. And what's worse is that all that extra traffic could overwhelm your service right when it comes back, causing a new outage. So, outages happen, they eventually recover. Recovery can cause thundering herds of users, which in turn causes performance degradation or further outages. You can't necessarily prevent outages, from the app side at least, but you might be able to do something about that synchronized traffic. One source of retries and synchronized traffic in an outage scenario is your users. So I suggest you defang your refresh mechanism if you can. Just make it do nothing if a retry is already happening. Most users aren't running your app under a network traffic sniffer. They're not going to know. The other source of retries is going to be your code, because someone presumably had the bright idea of automating the retry process. If you've been mishearing my talk so far, you may be tempted to take all control away from your users because clearly it's the humans that are the source of synchronized behavior and you know better. Let's dig into how this can go wrong. Here I show a basic approach, which is surprisingly common. Not the basic part, the approach. The idea is you try a request. If it fails, you repeat it immediately. And if that fails, you repeat it again, and so on and so forth, without any sort of limit. Now, if you want your users' iPhones and your backend both to turn into photogenic Martian craters like this one, I recommend this algorithm for you. And the reason is, it's not even a synchronization problem. The main danger is that this is very likely to turn into an infinite loop, a tight infinite loop. Why? Well, you may think that errors are always slow, right? If an error happens when you're trying to fetch a web page from somewhere and it just takes a long time and times out so all the errors that are going to happen, right? Well, no. There are many ways services have outages. Sure, servers can just stop, or the power or network cables can be pulled, or you can have timeouts. But they can also just be misconfigured, or maybe they can't reach the database backend to serve the data that you need. Or maybe the CPU is powered on, but the disks are failing and it can't read the disk. In such cases, the server might still be responding, but it would be serving error results. Error results and error pages tend to be a lot smaller and don't need to query data sources, because who wants to waste resources serving errors when you could spend those resources serving successes? By and large, errors are far more efficient and quick to serve than successful results. For example, a hit on the Apple homepage downloads megabytes of data cumulatively. But the 404 error page is a giant leap forward in simplicity, incredibly fast, and downloads a revolutionary 383 bytes or so. A lot faster. Right, so can we rescue the algorithm that we came up with before? What if we make it retry only so many times, preventing an infinite loop? Well, this too can be improved. Note that the retry still happens immediately. In practice, most conditions that cause one request to fail are likely to break the next one if it happens shortly afterwards. Random bit flips in memory, routing flaps in the internet, these are likely to last maybe a couple of seconds at least. So the next basic improvement is to not retry immediately. Let's chuck a sleep in there. This example waits for 3 seconds between retry attempts. You might ask, is there a recommended number of seconds? Should it be the same amount each time? These are good questions. There are 2 basic improvements on this algorithm, and it's best to use both of them. Firstly, observe that if something synchronizes the failures, such as recovery from an outage, then retries that happen as a result of the temporary load spike are going to be synchronized too. If a bunch of failures all happen at time t, then they're going to retry at time t plus 3, and any that don't succeed that time are going to retry again at t plus 6, and so on. To smooth off the retry spikes, it's best for each client to wait for some random amount of time before retrying. Secondly, outages and poor performance are often related to load. If the load is so high that performance is bad, or that causes an overload outage, then the total load needs to be reduced in order to recover. And it turns out that people who designed Ethernet, the networking technology, faced a similar problem. How to share a communications channel where multiple simultaneous transmissions could happen. Such transmissions would collide, garbling each other. In order to meaningfully reduce the chances of collisions in Ethernet, or for our purposes, to meaningfully reduce load on a service, the wait time between retries needs to not just be increased a little bit, but be multiplied. A common choice is to double the wait time for each retry. Combining these 2 basic ideas is how we end up with binary exponential backoff, which can be summarized as wait for a random amount of time between 0 and 2 to the power n, where n is how many retries we're at. It's a theoretically reasonable approach, it's widely used in practice, and finally your request library might already be able to do this for you. Here's how this might look when retrying an NS URL session in Objective-C with a Grand Central Dispatch. Since the font's probably tiny on your screen, I'm going to quickly take you through the main points. First, count the number of retries and use it to prevent an infinite loop. Secondly, double the maximum wait time per retry. That's the one double left angle bracket retry in this code. Thirdly, use a random number generator to pick an offset up to that limit. Here I use arc4random_uniform. And finally, use dispatch after to asynchronously dispatch a retry block rather than sleeping the thread to wait with something like ns thread sleep for time interval. If you sleep the thread, that would prevent other work on the queue from happening. But if you use dispatch after, no problems there. In Swift, you want the async after func of dispatch queue. In my previous code, basic doesn't have libdispatch, so we've got to make do with the sleep. Another thing your app might do is to proactively fetch some data every so often, or ping the backend to see if it's up. Once again, here is the most basic algorithm I could think of. Again, this is probably the worst option, so let's not spend any longer on it. We want to do something every so often, so let's chuck a sleep in there. In this example, we're trying to fetch something roughly once a minute, but that depends on your needs. Is there a problem with this? You might think that if each instance of the loop starts at a random time, and the loop always takes 60 seconds, then the aggregate traffic's always going to be smooth forever, and there's going to be no load spikes, right? But you may be thinking at this point that there's probably a catch. And you should be glad that it's not obvious. The problem is similar to this small physics demonstration from the UCLA Department of Physics and Astronomy. Here on the board we see a set of 5 metronomes. Each metronome influences the wobble of the board a little bit, which in turn influences the other metronomes on the board. Analogously, we can think of each metronome as like someone running your app, and the board and cans are your backend service they're depending on. Now in our loop, the 60-second sleep time is fixed, but the time to do a fetch varies. And one thing that greatly affects the fetch time is the load on the service. When slightly more fetches are in progress, that causes the fetches to finish a little slower because there's more load, making the loop iterations on those clients take slightly longer, having the effect that the end times of those fetches that were slowed are brought closer together. This causes them to become more in sync, forming a synchronized group. And the synchronized group is now routinely running slower than normal. Gradually, the group absorbs all the other clients because their relative offsets gradually drift over one another, leading to total emergent synchronization. So what are we going to do about that? Well, the basic solution to this emergent synchronization problem, most people pick the cron approach, or variously you might think of it as the Windows task scheduler approach. That's to do something at the top of every minute or every 2 minutes or so. And that's determined by the computer's real-time clock. In this example, the program performs the fetch at the start of every minute, when the second count is 0. It sounds nice if you believe the system clocks of your users are as varied as the clock on my microwave or car or VCR. Note that my microwave is definitely not a reliable source of time. However, modern computers and iPhones in particular are likely to have fairly accurate clocks. I don't mean accurate to the level of an atomic clock, but generally they're probably off true time by maybe a few tens of milliseconds. And even better, they are kept that way through automated synchronization processes. So as a result, while you probably won't break your service just testing one instance of your app, once lots of users are using it, you should expect a lot of traffic to happen all at once, followed by the rest of the time period, practically nothing. To serve all of those requests without them timing out, you would need many, many times more server capacity than you might have planned for, which is sitting idle the vast majority of the time. Once again, the basic solution to this problem is to add a random offset. Either of these methods is pretty reasonable. On the left, the algorithm picks an offset once, and on the right, it picks a new random offset each time. Now, neither is particularly better given a good clock. The left side is much more regular per client, but might be prone to clock synchronizing due to clock drift, if that's a possibility. For the price of one line of code, the right side is practically impossible to lead to any kind of synchronization problem. Finally, I have a couple of things you can do if you're lucky enough to control both ends of your app. That is, the client side as well as the server side. You might think that there's a way for your server to tell your clients to go away, and there is. If you're using HTTP, it's status 429 too many requests. There's a response header with this indicating how long the app should wait before it retries. Your RPC library of choice might also have such a response code. I don't necessarily recommend this for all apps, especially if you can't guarantee that all the apps are going to be coded correctly. At minimum, the ones that don't understand this code would just retry sooner than you want. And if you rely on that this behavior to be obeyed, you should rethink that. Another thing you can do, if you have multiple clients requesting the same thing at about the same time, then in addition to caching, which is highly recommended, you can do tricks like request coalescing. The basic idea is that if they arrive at similar times, they can probably be processed as one, rather than doing the same work for each one. Right? One approach might be to delay the handling of the first request to see if a few more come in. Another approach might be if your processing takes a while, just wait, just during that processing time, whatever ones come in, get the same result. Note though that this does require care. The code can be a little bit tricky, but also you shouldn't ever coalesce requests between users if the data being requested should never be shared between them, such as requests that return private information. You can also use a pattern like push or publish subscribe variously. An example of this is the Apple push notification service you might be used to. Normally, push systems are used to deliver messages in close to real time, either because you want to keep downstream systems as up to date as possible, or because humans are on the receiving end and they just love to be kept as up to date as possible. But there is a server-side benefit to this as well. By forcing the app to wait for pushes, rather than having them all poll regularly, the server can more directly influence how much traffic the system as a whole needs to handle. For instance, the server can send messages at its leisure up to a tested rate limit, avoiding network overload. But be aware that this isn't a magic bullet, especially if you're required to complicate things a bit by pushing messages within a certain time frame, or you're required to ensure delivery. In such cases, you may find a need to have a mixture of both push and pull, or you may find your servers overwhelmed with lots of client connections, large backlogs of messages to be delivered, or many messages that still need to be sent simultaneously. In conclusion, I hope you've learned something about thundering herds and emergent synchronized behavior, or at least have something interesting to think about. And if there's one takeaway from this talk, I hope it's the proverb, anything that can synchronize will synchronize. It served me well, and I hope it serves you well too. Thank you. Enjoy the rest of the conference, and I hope to see you all in the real world soon.